Our speaker tonight is Dr. Frank Marchis. Dr. Marchis is a senior planetary astronomer and chair of exoplanet research at the SETI Institute, the chief scientific officer at Unistellar, and a scientific advisor at VR2 Planets. Dr. Marchis is a pioneer in adaptive optics systems for ground-based telescopes and has utilized this technology to discover multi-body asteroid systems, study the volcanism of Jupiter's moon Io, and search for exoplanets. He has also developed algorithms that enhance both the macroscopic images acquired through telescopes and the microscopic images acquired, the microscopic images acquired through microscopes. He's helped develop space mission concepts and is a member of the SETI Science Council, the Gemini Planet Imager Steering Committee, the 30-meter telescope science definition team, the PLOS One editorial board, Project Blue, and the Planets Foundation Advisory Board. His research has led to 75 publications in major journals, including Nature and Icarus, and hundreds more where he is a co-author. In April 2007, asteroid 1989 S08 was named 6639 Marchis in recognition of his work in the field of multi-body asteroids. He's also been a science consultant, has been interviewed in several documentaries for the Science Channel, the BBC, the French-German television network ARTE, and news media in English, French, and Spanish. His academic research is currently focused on developing new technologies capable of imaging and characterizing Earth-like exoplanets, and the education and outreach activities associated with these efforts. Through Unistellar, he is also helping develop products that make astronomical observation more accessible and enjoyable for a wider audience, and that provide opportunities for more people to participate in citizen science. Please, at least in your minds, give a very warm welcome to Dr. Frank Marchis.
Thank you, Mark. Can you hear me all well?
Yep, you're coming through clearly.
All right, great. This is challenging, so I don't know if you can see my camera, but I'm in the dark right now because I'm in France, in fact. I'm in Europe. I poorly planned this and decided to fly to Europe just before this talk. But anyway, it's also an opportunity to speak to you again, and I'm very glad to see that you are healthy and everybody is smiling and happy despite the situation, because the stars are still here, right? And that gives us hope. So today I'm going to talk about the citizen science network we are putting in place with Unistellar network. So you probably remember last year, I think, or 2 years ago, I came to visit you in Portland and I show you the EV-scope. But at the time, it was cloudy, so we could not see through it. And that was a prototype. But now we are more than a prototype. In fact, we have shipped and we continue shipping those EV-scopes around the world. So let me remind you, first of all, this is the list of my collaborators. You may know some names here, but I want to point out that Tom is the lead of the exoplanet group. Dan is a great student working in our team on education for exoplanet, and Joe works on planetary defense, and everybody else here is involved in some part of the project. I'm just showing you the work of a lot of other people here. So I'm in France because the Unistellar company is located in France, in Marseille, in fact, and we had our retreat, our yearly retreat. And it's incredible to see how we grew in size over the past 2 years. We are now almost 40 employees, and this is basically the people of Unistellar France. So we have also offices in San Francisco, which is basically leading the education, communication, repair and service of the United States and Canada. So what is Unistellar? So Unistellar is a company which is developing a new type of telescope, a telescope which is smart, robotic, easy to use, a telescope for everybody. On the top of building this telescope, we are generating data. These data are scientific data, and that's what I'm going to talk about essentially today with you. So this is the team at the SETI Institute. So SETI Institute is our scientific partner. I'm a researcher at the SETI Institute, so that was an easy to be the connection between the two, the private company, the non-profit organization. And this is a team of people working with us at the SETI Institute for the research itself. So as you can see, it's mandatory to pose with an EV-scope if you want to be part of the company. It's not. It's if you receive one and then you have to show that you really like it. But it's a great object to show around, definitely. So the EV scope stands for the Enhanced Vision Telescope. It's a consumer product telescope. We built this telescope with the idea of bringing back astronomy to people, even in cities. So it has what we call the enhanced vision, which is basically a system of stacking live an image to improve the sensitivity of the image. So be able to see in color galaxy nebulae and comets. It's a portable telescope. You can carry around with a backpack. It's compact and it's easy to use. And there's this kind of innovative design because it's a telescope, but it's more like a camera as well. It has integrated the CMOS detector. You control it with a phone, and that make it easy to use for the younger generation, of course. It's also an educative device. You don't need to know much about stars. The first time you use it, it will basically guide you and tells you where to point, what to observe. He has a library of 5 million stars in memory, so he does what we call autonomous field detection, which is split scaling in real time, and he can find where it's located, where it's pointing, so give you the list of targets that could be interested for you. And it's connected thanks to the fact that you're using it with a cell phone. So the cell phone can receive information almost in real time as you're observing. You can get new targets. You can improve the database inside the telescope so you can see new targets. And finally, it's useful for science. And that's really the main reason I'm involved in this project. It's useful for science because of its sensitivity, because it's accurate enough to point to the right location, and because of the campaign modes we are developing. So that's what I'm going to essentially talk about today. But before that, just the technology briefly. I know I talked about this last time, so I just want to mention, so you have a CMOS detector, an IMX224. It's a Bayer matrix detector sensitive to 3 colors. So that allows us to get color images. It's basically a Newtonian type telescope with a sensor located at the prime focus. So the light comes to the primary mirror, which is a 4.5-inch mirror, bonds to focus to the sensor, which is a CMOS detector. The image is collected by the onboard computer, which analyzes in real time the image. So the analysis could be removing the background, checking release vibration, and wind introduced by wind, or people moving the telescope, or anything like that. And the computer is also acquiring images with an exposure time of 4 seconds in enhanced vision, an exposure time of a few milliseconds in live view. And then what we have an electronic eyepiece, which basically is a projection device. It contains an OLED display screen with some optics to give you the same feeling like if you were observing the dark sky. And this allows the user to see in the eyepiece and see where the telescope is pointing as well. And I think that's an important part of the experience. We don't want people to be glued on their phone only. We want people to come close to the telescope and enjoy together seeing through the telescope and knowing where the telescope is pointing. I must say, I think I admitted that to you last time. I learned more about the constellation and the stars since I have an EV scope that I had my entire life as a professional astronomer. Because this telescope, I use it a lot, and I also know where it's pointing. So now I finally learned the constellation. Some amateur astronomer told me recently that it was about time after 25 years, right? So, and the software is also an important part of the telescope. We do have what we call the autonomous field detection that allow the telescope to know where it's pointing and to identify a target in the field of view. So we have in the database those millions of stars to do this, but we also have Messier objects, 8,000 NGC targets, 4,000 asteroids, all the planet as well. And we are increasing the number of targets on a regular basis and increasing as well a description of those targets. See, for those who have the telescope, you may have noticed that we are adding more and more targets description into the app. And that's the idea of explaining to people what they're observing. I mean, it can be a lonely activity to observe, and if you will get an observation of a comet or a galaxy, but having an explanation at the same time coming from the phone, short but clear, allow people to really understand what they're doing and also to give star parties outside. So instead of explaining what we can see, I'm going to ask my colleagues, Val. Val, are you here?
She was here.
I'm here.
There she is. Okay.
So Val is located. So Val, first of all, is part of our team. I forgot to show the picture of you, but maybe you have a camera.
It's okay.
It's okay. Sorry, Val. So Val is located in Maryland because we love creative things at Unistellar. So she's located in Maryland right now, and in a Sky Border 4.5, and she will be able to basically show the telescope in action. Is it weather still clear, Val?
Yeah, it's a little bit windy though.
Okay, well, let's try. So I'm gonna stop sharing. You can start sharing your screen.
Okay.
I have picture anyway. So this is, so I stop sharing my screen now. You can start sharing your screen so people will be able to see your app on your phone.
Can you guys see that?
Yes. So right now we are pointing to, go ahead.
Oh, it's M51, the Whirlpool Galaxy. I've been doing this for about a minute now.
Okay. So this is with the 4.5-inch telescope. It's live, it's 1 minute exposure. So the first 2 or 3 minutes are really good because you can see clearly the image getting better as the telescope is collecting and stacking images. Of course, the limit of that is the background of the sky and the seeing quality of the sky as well. But you can see the spiral arms and the secondary galaxy. This one is located. Can you show us the information?
Oh, sure.
So this is what I meant by I say we have information. So you can basically read this. There is a short description of the galaxy, and this is in the landscape mode on the app. So that's a M51 called the Whirlpool Galaxy, etc., etc. Then there is a dwarf galaxy nearby, which is in gravitational interaction. But you know this target way better than me, of course. I'm a planetary astronomer. I'm not a galactic astronomer. Can we do another object so we can show people how it works? You decide, since you know the site and you know the visibility in your site.
Okay.
So you go ahead. So you go to Explore menu.
Sure.
You go to Explore menu. You enter the dumbbell. So you know by memory the dumbbell number. But can you go to the menu where we can see the preferred targets, the recommended one? So here you have in the recommended menu all the targets, all the galaxy which are visible from your location. And if you go back, you can show, there is also, there is also some globular cluster, open cluster, nebulae. Let's go to nebulae since you want to go in nebulae. So there is M87, which is visible at the moment, but you decide to go to M27, 157. Go ahead.
There it is.
Okay, so the telescope is slowing to the Dumbbell Nebulae. As you can see sometimes some stars in the field of view. In the meantime, you can read about the Dumbbell Nebulae. What is this nebulae? What's the age, the distance, and so on. So what you just have to do to set up the telescope is to basically level it first. You level the tripod, and then you set up the telescope, and in less than 2 minutes, it should be ready to observe. In fact, some users are doing a competition in a video time lapse showing how quickly they can set up that telescope. And I think someone did it in less than 1 minute and 30 seconds. But so now the telescope is more or less in the field of view. He's been slowing down. He analyzed the field of view in real time, and he's gonna move back and forth. So depending on the brightness of the sky, the length of the motion, it will take more or less time. Let's see. So it's still slowing. This is the analysis of the field of view, counting stars, looking at the location. I think it knows where it's located right now. So we're trying to make this as easy as possible. So that's why we don't know much about what's going on, because we don't want to bombard people with information. There will be a pro mode where people can basically know exactly what the telescope is doing, how many frames it's analyzing, and so on. But right now, the app is made for everybody, trying to make it simple as possible. So the GoTo has been validated, meaning that the target has been identified. So Val is activating the enhanced vision. So the first 4 seconds is basically an analysis of the frame, and boom, wow, not bad at all. So we are in the Milky Way. So there's a lot of background stars, but not too far away from the Milky Way. So this was the first image. This is the second image. And you can already see some color popping up on the screen. Excellent. So you can even see the central part of the planetary nebulae already on this third or fourth image. So the image can be saved. Can you show us how you save it, and what do you save it with the label? I don't know.
Yeah, so there's 2 different ways to save it. You can save it on this button up top, which creates the circle and information about the image. You can also take a screenshot. Oops, sorry. Here we go. And take a screenshot like that to get a larger view as well.
And we are improving the software on a daily basis. In fact, the app, the internal software, and the app as well. I saw the new app, for instance, last week, and there is a lot of very good things in it. You will like it, Val.
Cool. Such
as the identification of the constellation, where the object is located, and so on. So that's gonna be, this is the main thing. We spent 2 years developing the telescope. Now the telescope is ready. The app is truly what we are focusing on to make it more easy, stable, of course. There is still some issues from time to time, but also more connected to what people want to see while they use a telescope. Thank you very much, Val. I can continue my talk, and if you want, we can go to a faint target, like, I don't know, the Boat Galaxy or something like this, M16, M17, yeah? And
sure.
When you have the image, you let me know, and I can show the audience, yeah?
Sounds good.
Okay. All right, thank you very much. So I'm gonna take back this share screen. Okay, I'm back, hopefully. So you have seen it in action. So this is some of the observation we collected when we were testing the telescope. So you have gallium 51 and 27. Something which is extremely important to say is that the telescope has a better image quality into the eyepiece. It's an experience that we really need to focus on. We're trying to make sure that people look through the eyepiece and the image is better because the quality of the screen of a phone is not as good as the OLED display that we have on in the EV scope. So some of the observation you see, I show you here, kind of mimic what you see in the eyepiece. Of course, we have to see the telescope to see that. So our users have been using the EV scope since they received their first models. We started shipping end of 2019, and we have shipped now more than 1,000 telescopes. Sorry, or soon 2,000 in fact. So this is the Orion Nebula on the left, taken by Alain Vézina in Quebec. Julien Bérard is observing also planets, so that's Uranus and the satellites. We have observers in the southern part of the world where the stars are beautiful and there is a lot of interesting things to watch, such as the Trifid Nebula and the Lagoon Nebula. So this is from Réunion Island. We have those observation of a galaxy, I think is a M100 here, and of course comets. A lot of comets have been observed recently with the EV scope. So something which I really like is that our users now basically trying to do, trying to basically find new challenges. I mean, they've been observing the objects in the database, but the telescope can point anywhere. And so we have some users who are trying to observe the most distant object with the EV scope. So one of them is Frederick Davis. He's an astronomer, but he's a theoretician astronomer, and he loves using his EV scope because it's an easy to use telescope for him, and he's been working in the field of cosmology for years. So he basically tried to observe this quasar PS1. I'm not gonna read the number. The main part here, it's a very distant object. He has a redshift of 4.3. So we're talking about something that which is located 12 billion light years away from us. So from his garden, and I think that was in Arizona, so from the garden of his mother, he's been able to detect, you can maybe see it here if you look carefully, an object which was formed 1.4 billion years after the formation of the universe. I mean, that's something I know it's a tiny dot far away, but it's incredible to me that with a small telescope like the EV scope, we can see this now. And I'm glad that people are getting imaginative and do more and more of these challenges with the telescope. So this is the telescope open and ready to use, and this is what it looks like. This is the backpack that you can use to carry it around. So it's 10 kilograms. We have also people who set it up into a kind of suitcase, and they can drag it around as well. So it's easy to use for star parties as well. So you have seen the app, so I'm not gonna go through that again, but that's what the design of the app we have at the moment. Neat, simple, easy to use, and of course there is some improvement to do, but we are working on that software. Okay, so my contribution to this project is more into the science. In fact, I joined the company as a co-founder after it was created, because I brought the scientific part of the project. I've been working for years with what's so-called amateur astronomers, which are not amateurs and not at all. They are as good as professional astronomers, except they are not paid for that. So we call them now citizen astronomers, because those are people who know about astronomy as much as professional astronomers and spend time to observe the sky in partnership with professional astronomers. So you probably know that as professional astronomers and amateur astronomers been working together to find, for instance, comets and asteroids, a significant number of comets Last year, I think 10% of the comets have been discovered by amateur astronomers, in fact. So despite of the large survey we have in the professional astronomies, we still need to have those eyes looking at the sky continuously and often to be able to find interesting targets. One of them is Churyumov-Gerasimenko, of course, which was the target of the mission, of the ESA mission. But more recently, the interstellar messenger, the Borisov target, has been discovered by Borisov, who is an amateur astronomer from Hungary, I think. And that's a significant discovery. That's the second interloper ever discovered. So I'm, again, with this community of citizen astronomers, we can do major discovery. And that's the motivation of the Unistellar network. So we started a partnership with the SETI Institute in 2017. So the SETI Institute is a research institution in Mountain View, California. And we have been working for years in citizen astronomy, involving the public in outreach, in our research. So that's an easy partner for Unistellar. The goal is the SETI Institute will basically curate requests coming from professional astronomers and send notice when something interesting happens in the sky to the network. The data are collected and sent to our servers. We analyze the data and we send back to our users or citizen astronomer a report describing their contribution, their scientific contribution. So we have identified a large number of science cases that I'm going to show you here today. So concretely how it works, well, this is the way we're imaging it at the moment. And of course, it's not yet implemented, but we are working on that. So you're observing, or you are going to observe in the next days, you go to your app, there is a menu for science. You have pre-selected some scientific topics that are interested to you, such as comet, comet occultations, transiting exoplanets. So you will get an alert when something interesting is happening in the sky. A new transit, some requests for observation of a comet. This can happen a few days before, it can happen as well while you're observing. So you point to the object, the telescope will basically have predefined observation modes for the scientific observations. So the telescope will basically acquire data. You can see in the eyepiece data being taken. And after the data are taken, you send the data to the SETI center. We analyze them and we send to you back a report. That could be an animation, a figure, a trophy, etc. So we identify 4 specific science cases that we are working on at the moment. There is more, of course. One of them is planetary defense, is to protect our planet against asteroid strike by identifying and monitoring those asteroids that could potentially impact our planet. We have asteroid study by occultation. In this case, we don't see the asteroid, we see the shadow of the asteroid. So we observe a star that will be occulted by an asteroid, and we ask our user to do that simultaneously. And if they're located on the band of visibility, they will see the star disappearing for a short amount of time. And by combining this observation, we can get the projected shadow of the asteroid, so the size and shape of the asteroid. Then we have exoplanet transits, so to basically confirm observation of exoplanet detected by TESS and future missions. And finally, what we have the transient events, which are a little bit of everything, which I may discuss later in more details. But that include the detection of the afterglow of gravitational waves or gamma ray burst, but also the crazy part of the SETI research, which is the search for laser beam sent to us by extraterrestrial civilization who want us to know that they are there. So in planetary defense, we started this program very early. In fact, in 2017, that was one of the first scientific observations I did from my garden. I observed 1999 KW4, which was having which was visible enough at the time, magnitude 15.2, that you can see here in the middle from San Francisco. Of course, we have more observation taken since then, but what is very important is that this observation show the presence of an asteroid, near Earth asteroid passing by, moving with respect to the background stars. That's why you see those tiny lines in this case, because those are long exposure. We have an accuracy of 0.4 arcseconds on the position of the asteroid. So the community of planetary defense has been relying significantly on citizen astronomers. If you look at the map on the left here, you see that a lot of professional telescopes are in United States, in Hawaii, and in Chile. And then there is very few of them, for instance, in the east part of United States, in Europe, and in Asia. So in fact, this gap has been filled up so far by observation from citizen astronomers, people who have a 30 centimeter telescope or even bigger in some cases, and which use the MPC alert system to observe and confirm the existence of those asteroids. Because our survey sees them once and then send an alert saying this is an asteroid candidate. And those amateur astronomers will basically spend the time trying to track it, find it. And as soon as they find it, they send a new position. And this new position is used by MPC to calculate the orbit. And in some cases, to even calculate the location of the impact before a few days or a few hours before it occurs. So this, we want to basically integrate the UV-scope network into this network as well. So we developed a tool that monitor continuously asteroid candidates coming from 3 sources, MPC, ESA, and CNEOS, which is a JPL, and send us alert. So now we know when an asteroid is visible by the unistellar UV-scope. I did not mention, but our sensitivity limit in cities is typically 16. We know we can go deeper and fainter in the countryside. We have tests that validated up to magnitude 17.5, but right now we're trying to be very conservative. So this kind of asteroid, bright enough to be visible from with an UV-scopes, happen basically once a week in average. So as soon as one is detected, we will send notification to the network, and the network will be able to observe almost at the same time the asteroid flybying Earth. And we collect the observation and send this observation to MPC and other repository center that will basically quickly calculate the orbit of the asteroid. So we have done tests. This is basically 1998 OR2 passing by, when he was flying by Earth, he reached magnitude 11 for this one. So that was a very bright target. This is an observation from San Francisco when it was magnitude 14.5. So you can see it moving here. We also characterize this asteroid by doing Likers. That's what you have here. So right now we're running a pilot programs with for main belt asteroid, but we also identify some interesting MEOs near Earth asteroid, Earth object that will be observable with the UV-scope. So if you have an UV-scope, you probably may have received from us some of this notification of a new object to observe. And there was last month, we had 10132 and 1120, for which, because we wanted basically to show that even if an object is magnitude 14 or 16, we can still see the variation of light due to the spin of the object, and then confirm the rotation speed, but also provide information on the shape, and maybe the shape and the binary shape if there is 2 components of the system. So this is a pilot program which is working very well. We're making a lot of progress on a daily basis on this. So the second program is the study of asteroid biooccultation. We did the first observation in September 2018. That was in January 2018. That was Andromaque here. So in this case, you observe a star and the star disappears. We have the flux here. This is the life curve. This is the flux and the drop due to the fact that the star is disappearing, and then the star reappears. That was done with the prototype, which is here. I did the same in September 2018 for Sappho with a 7.5 magnitude star. You can see a sharp drop here. And from this timing of the ingress and egress, we can basically get an idea of the size of the asteroid because you know the motion of the asteroid with respect to the background star. One thing we did in August 2018, we moved to San Diego to observe here an occultation by Pluto, the dwarf planet of a 13 magnitude star. So this is basically the team. So what you can see in the background here is myself with the prototype. And what you see in the foreground here in the C14, an EMCCD camera, a computer, an astronomer coming from Paris, who did the observation. And this is the light curve obtained with the C14. And this is the light curve obtained with our small telescope. What's interesting here is that we do have a detection of the atmosphere of Pluto, because the drop in light is not sharp, like you can see here, and this is due to the refraction of the atmosphere. So by analyzing this kind of light curve, we can derive the density of the atmosphere of Pluto and even detect some areas which are not homogeneous, some turbulent parts, for instance. So this data is still being worked by the team of the Observatoire de Paris. They're combining basically 40 observations collected during this event to see if they can get information on the contraction of the atmosphere of Pluto, since Pluto is drifting away from us due to this elongation. So now we do this on a regular basis with our industrial version of the UV scope. And I wanted to show you some of the pictures collected by our user over the past 6 months now. We travel with the UV scope to do some observation. We have done a lot of negative chords. That's part of the game of occultation, but we also have positive chords like Tekla here and more. Let me show you some of them which are interesting. This one was observed, that's the first one, in fact, observed by an amateur, a citizen astronomer. Morand Studer is in Brittany. He bought a telescope through our Kickstarter 2 years ago, and when he received it, he started observing occultation that we sent him as an alert. And that you can see here. That's the disappearance of an 11 magnitude star that lasted 0.3 seconds due to 2000 UD52, which is a small 7-kilometer asteroid in the main belt. That's the first time, in fact, we have an occultation by this asteroid. It's not much, it's just a tiny dot disappearing. But from this tiny dot disappearing, you can see here, those are called chords. You can basically have a very good estimate of the location of the asteroid. And this is the first step. Being able to see an occultation once gives us a way to nail down the position of an asteroid very accurately. And then after that, you can refine the orbit so well that you can predict better. You can better predict occultation in the future. So we are starting this with more and more asteroids. In fact, we have detected already 4 occultations, 3 in Europe and 1 in the United States, using our network. And thanks to the contribution of those citizen astronomers. Morand Studer is not an amateur astronomer. He told me he bought a telescope a long time ago that he rarely used. And then he bought the UV scope because he was interested in the concept. And also he liked the idea of being able to contribute to scientific observations without spending too much of his time on the technology, but more on the observing. So that's what he did. And he did that during the confinement in France, which was very strict. So he could not get out of his house. So basically, he was very lucky to have the centrality band just passing above his house. So we have been also working with NASA and the Lucy project on occultations to characterize the Trojan asteroid that will be visited by this mission in the future. So there was 2 of them, Horus and Locus, predicted in September and December. And in fact, we sent a team in Oman. That's something you can do, is like send out of the blue a team of 3 people with 3 telescopes. 2 of them arrive in Oman. I spare you the details of what happened for the 3rd one. But anyway, we basically have, we follow the indication from Mark Bouy from SWIRI. And we basically located 1 telescope exactly in the middle of the centrality and 1 slightly outside. And in fact, we detected, you can see it here. If you look carefully, it's gonna disappear. This one here, let's do it again. Boom. So the event lasted 4 seconds, and that's what you can see here. And that's the first time we detected an occultation by the asteroid Horus. So we have an estimation now of the size of Horus, which is 45 kilometers. Of course, NASA liked that because it's a very low-cost way of first it estimated accurately the position of an asteroid. And that's very useful if you send a spacecraft to fly by it, of course. Get information about the surrounding, about the asteroid itself, its size and its shape, and also see the surrounding of the asteroid. If Horus was a binary system, we could have seen 2 blinks here due to the fact that there is 2 components in the system. So we did not see that, so we're confident that Horus is in fact a single system, but more observation need to be taken using the occultation techniques to truly understand the surrounding of Horus. Okay, so I'm not going to go through that, but that's just basically the way we do this occultation at the moment. We predict them using different tools, plus scientific personal communication I'm getting from the Observatoire de Paris, from SWIRI, and other people who are interested in occultation, like Lucky Stars. We request observation to our citizen astronomers with using email and Slack at the moment. 40% of them successfully observe the occultation. That's always, there is always something that can happen, wrong coordinates, bad weather, you name it. Something always happens when you do occultation. The data are sent to us, we analyze the data, we process them first, we analyze the data, then we send the data to Euraster and IOTA, also to the scientists who requested the observations, and citizen astronomer receive a notification. Receive the light curve, but as well, but also some kind of trophy to show his contribution or her contribution to the project. So as I say, we're doing now occultation on a regular basis. We do 2 per week in Europe and 2 per week as well in the US. And the network is expanding to Japan and Australia. So we expect to do as well 2 per week in those in this part of the world. Okay, another science cases is the observation of transiting exoplanets. I have no idea how long I've been talking, so I'm just gonna simply mention to you that exoplanets can be detected through various ways. We know 4,000 of them. Most of them have been detected by transits, meaning by the attenuation of light due to the passage of a planet between us and the host star. We did the first observation of an exoplanet using the EV scope. There was HD 209458b, which is famous because that's the first exoplanet ever discovered by transit. It's a very bright star, 7.6 magnitude, and the planet is large, several times the mass of Jupiter. So you can clearly see here the attenuation of the flux in blue with the EV scope. And this is a comparison in red with another telescope taken at the same time. So we're doing more challenging things now. We are targeting fainter stars because we are trying to show that we we can basically confirm target test object of interest. So we have been detecting one of them, which is also called Qatar 1b. It's a Jupiter-sized exoplanet, and this is the light curve collected by a citizen astronomer, Julien de Mailly, who is basically located in Switzerland. And he observed that from Lausanne, or nearby Lausanne. So that's the first time a citizen astronomer using the EV scope detected and validated the existence of an exoplanet using his EV scope. You can clearly see the attenuation. Here, we calculate from this light curve, the blue dot here, we can extract the depth, but also the mid-time transit. So our goal is to basically help NASA with those projects. As I said, there is 4,000 exoplanets detected so far, and there will be significantly more. TESS, which was launched a year and a half ago, already detected 1,600 objects, and 200 of them can be confirmed using the EV scope. So the first step for us is to confirm the largest exoplanets observable with the EV scope. And the second step is to monitor them, to refine the orbit, so we can provide accurate ephemeris in the future of transiting exoplanets. And why do we care about this? Is because we are launching expensive missions, such as JWST, RCA, and so on, that have been made for that, to observe in spectroscopy the transiting exoplanet, to analyze the atmosphere of those exoplanets. So they need to know when exactly these events will happen. So what we are doing with this small array of telescope is to monitor continuously those transiting exoplanets. So in 3-4 years, we'll be able to tell professional astronomers when exactly a transiting exoplanet will happen. So you can request JWST time only at this moment, and not like 2 days before and 2 days after. That can happen, which is typically what you expect because of the propagation of errors due to the ephemeris. We can also see the surrounding of an exoplanet, so detect rings. This is a simulation of a ring around an exoplanet. And we can also see some small variation of the mid-transit time due to the presence of multiple planets in the system. The same way that Neptune was discovered, for instance, we'll be able to detect super Earths in systems by simply measuring the variation of the mid-transit time and see, and from this small variation, estimate the mass of the perturbator. So they see if there is a super Earth in the system. I think it's extraordinary that the technology has evolved to the point that someone with a small telescope in his garden contribute to such a large and important scientific research, which is the detection of super Earths in planetary systems, which are located 100,000 light years away from us. When I say it again, I still can't believe that we are reaching the moment in history where people can do that. And I think it's great and give me faith in the way the world is going. So this is complicated graph, but the point here is that those observations was done with one EV scope. Now imagine what will happen when we will ask 100 EV scopes to observe the same transit. So we are working on that, in fact. We're working on combining observation from multiple EV scopes. So we refine, we get a better sensitivity. And what we have shown is that in this case, we get a better mid-transit time, which basically, the error is basically vary with the square root of the number of telescopes. So it means that in the future, we have right now an uncertainty of 5-6 minutes on our transits that we have observed. So it means that in the future, we can get quickly less than 3 minutes. And that's exactly the kind of perturbation you expect if you had a super Earth in orbit around, in a planetary system where there is a Jupiter-sized exoplanet. So when I mentioned that we will be able to detect super errors, it's not science fiction. It's truly what's possible right now. Okay, I'm gonna skip this because I've been speaking way too long. And I'm just gonna say that we, once again, not trying to do everything from scratch. We basically collaborating with the Exoplanet Watch led by JPL. And they basically use data coming from various surveys such as TESS and NASA Exoplanet Archive to generate alerts. So those alerts are sent to the community of amateur astronomers. So we are using them as well through SETI, which to coordinate observation using our EVScope network. These data are processed and stored by the Exoplanet Watch and AAVSO. And of course, the goal is to combine observation from multiple sources, EVScopes or others, so we can get do a global analysis for some of those systems and refine the timing, derive the ephemeris with an extreme accuracy, and of course, see if there is anything interesting nearby this exoplanet, such as rings or exomoons. So what's the next step? So the 2019-2020 was truly to manufacture the telescope and ship it. We're still in the process of shipping the units. We pre-sold 3,000 of them. So it takes a while, especially in the situation right now with the COVID-19. But we are confident that by end of September, we have shipped the 3,000 EVScopes, which has been pre-sold. We are continuing the manufacturing, but what really mattered to me is that we are putting together the science. So we have developed the occultation, the planetary defense, the exoplanets. It will be implemented into the app to make it easy for users to participate to those campaigns. That's truly the goal for the year 2020, to make the observation of the stars as the observation of the science as easy as possible, so people can contribute to science quickly and get quickly some return, some feedback about the observation, if it was useful or not, what kind of discovery we made, how this observation can be improved, etc. We want to teach people, we want them to be part of the network. They not just do the observation and then we forget about it. No, we want them to be active members. So that's why we created this Slack, and so they can communicate with each other, create their own network, their own scientific research if they want to. Right now, the data are not available, but in the next few months, we will make each user will have his own access to his own data. We'll be able to do his own data analysis as well. So I don't know where we're gonna be in 2021, but truly the goal is to do science and publish this result in journals involving our citizen astronomers as well in the process. So we have ideas of how we could involve them in the publication process if they want to. But once again, we are using the time of people. It's very valuable considering that they can do a lot of other things than using their EVScopes to observe a star. So we want them to take ownership for this observation and be proud of it and contribute more than just by their time, contribute as well by their brain, contribute by their knowledge as well. And I think it's important for the entire community of astronomers, professional and amateur astronomers as well, to involve people, especially the young people in our field. So we are looking for funding. That's what every scientist will end his talks by saying that we need more funding, but fundings could come from scientific institutions like NASA or NSF, or also private foundations, and we are working on this at the moment. And I would just mention that we are doing some fun stuff like combining observations of observers. So we organized, for instance, a campaign for the Comet Atlas in April, where we ask users to observe at the same time the comet. So this is a comet from my garden, here on the top. And this is the comet observed, combining observation of 20 citizen astronomers in the US. And this is the same with 40 citizen astronomers in the EU. So we can basically now create this virtual super telescope by combining these observations. We are working in making this better. This was our first attempt. We're sure we can do better than that, especially using smart data analysis, data processing systems such as AI or machine learning based processing. We also have people do some fun stuff such as unexpected one once again. So this is the observation of the sun to observe the Mercury transiting the sun. That was in November. We have observers who have been hunting for the International Space Station, transiting the moon and also transiting the sun. So we have some movie which has been released, and one of them got the attention of a very famous band called the Muse. They basically allow us to put the music on the top of the video, and the video has been shared and seen by, now it's not 20,000, it's more like 100,000 people in the world. Connecting astronomy with another field, like in this case, the music industry. I think it's important as well. And I will end here by saying that we have demonstrated that the EVscope can contribute to science in the year 2019-2020. The next step is to push this to another level by having more easier scientific program, maybe more targeted to some interesting research funded by space agencies as well, such as NASA, ESA, and so on. We're also discussing with informal education centers, so amateur astronomer clubs, library, museums, national parks, and the Girl Scouts of America. So they could have an EVscope in their hand and contribute to science. So if you're interested, please let me know, of course. And the network is being built. The network of citizen astronomers is being designed at the moment. We have some exciting new results. More will come in the future. And in fact, you don't need to have an EVscope to contribute as well to our network. There is a lot of other ways to do that, including helping us to curate scientific research, scientific cases, for instance. And we have interns who joined us recently to help with this. And the goal is to really make science and astronomy more fun and more attractive. We want to basically bring some new ideas and new people into this field. And I think on the long term, we're all gonna win from that. It's not only selling telescopes, not only enjoying making pretty picture of a planet, of a comet, and so on. It's also enjoying meeting and having some fun discussion about a quasar, which is 12 billion light years away from us. And I think this project is truly about this. It's creating a community, and a community that will take ownership of the research and the scientific discovery they're making. And I will end here.